Hi everyone, welcome to another T-Rex Classroom video series. I'm Adele, and today I'm going to be presenting about my project, The Power of the Sun, Exploring the Hybrid Inverter. Now a little background about this. This was a project I did for my Tier 2 application training, and something I just kind of researched and conducted tests on my own. So today I'll be sharing my overall test and my results, as well as my analysis. So quick content overview, I'm going to talk about the background, system architecture, test methodology, my results and analysis, and lastly, my conclusion. Now, what we see here is our first look at the system architecture for the hybrid inverter system. But before I get too far, let's talk about what is a hybrid inverter and why is it important. Now, in a home, solar panels can generate DC electricity, but homes and the utility grid operate on AC energy. So we need an inverter for the power conversion. However, hybrid solar inverter converts DC to AC while also managing battery storage. This allows energy to be stored and used later. Additionally, hybrid solar inverter has a bidirectional power flow between the battery system and the utility grid. So essentially, the hybrid inverter acts as the brain, deciding where it should have the converted solar energy go throughout the system. Now let's do an example. Let's say it's a really sunny day and there's a lot of solar energy coming from the solar panels. The hybrid inverter will take this and use it for power to supply the home or the residential load. And because there's a lot of solar energy, maybe there's excess power or excess energy being used or not used in this case. In this case, the hybrid inverter will take this extra energy and use it to start charging the battery to be used for later. Now let's say, for example, it's a cloudy day and there's less solar energy coming from the panels. In this case, there may not be enough energy to actually power the residential load or the home. In this case, the hybrid inverter will take energy and start discharging the battery to help supply power to the home. And in this case, if there's still not even enough, maybe the residential grid will start supplying and it'll take energy from here to help supply energy to the home. Now, with that said, my application or my project will be exploring the power efficiency of this inverter system. Now, you might be asking, how exactly do we calculate efficiency and what is it? Overall, efficiency is going to just be the power output over power input times 100 to get our percentage. Now, why is this important in our hybrid solar inverter? Well, efficiency in a system like this is key to minimizing loss, and having an efficient hybrid inverter system means we can optimize our solar power generation and distribution. This is really important in utilizing solar power to save homeowners from really high energy bills. Now, my overall mission that I was really exploring in this project was evaluating our inverter's efficiency by testing its 4 primary interfaces. So in this case, it's going to be the solar input, battery interface, grid connection, the AC grid, and the residential output, so like the residential load, and measuring how effectively power is converted and transferred across each of those pathways. Now, let's take a closer look at the inverter I'll be using. The device under test, or the DUT in this case, is the GEH51U US10. Now we can see over here, we have the max solar input at 15 kilowatts. The battery interface has a max charge and discharge rate at 5 kilowatts. The residential house has a load output at max output power of 5 kVA. And lastly, the US grid has a max power output of 5 kVA, input of 6 kVA. Okay, now that we know these specs, now I want to emulate the behavior of the solar array, battery, residential load, and the AC grid to best test the efficiency of a hybrid solar inverter. Now you might ask yourself, well, why do we need to emulate these systems? Well, I want to be able to perform controlled testing, and this allows us to isolate the variables to only test the inverter and protect other input systems. Now, I first want to talk about emulating the solar panel. In this case, I chose a 36-panel configuration of this specific type. To emulate the solar array, I selected the IT6018C. a bidirectional DC power supply, along with a specialized SES 1000 software. Now, the SES 1000 software is able to simulate IV curves under different irradiance and temperatures, which is needed for the varying solar output. Now, irradiance is basically just the amount of sunlight on a specific area. Next, I emulated the battery energy storage system. To emulate this, I used the IT6006C again, once again, the bidirectional DC power supply, along with the specialized BSS 2000 battery simulation software. The BSS 2000 battery simulation software lets us simulate different battery chemistries while charging and discharging and looking at those specific curves. In this case, I used the lithium-ion battery curve. Next, in emulating the AC power grid, this one in particular has 48 kVA or max power, but to actually emulate it, I don't need to do this full 48 kVA since it's limited to the amount of power our inverter can actually output, which in this case will be 5 kVA. Lastly, I'm going to be emulating the residential house load. And once again, this has a max power of around 10 kVA, but once again, we're limited to the inverter, which only has a max power output of 5 kVA. Now, to emulate the residential house load, I selected the IT8209, an AC electronic load. We have over here. Now, this diagram kind of shows the whole full test equipment system we have here. So over here, we have the IT8209, the AC load. So this is the residential house. This is connected to the inverter, which is also connected to the residential split phase grid, the IT7909. Then we also have the battery system here on the right and the solar array panel system here on the left. And we can see kind of the overall structure of how it would be all wired. Now that we have that, let's move on to test methodology and results. Now here I would like to make a distinction between my hypothetical and actual test setup. Now, up until now, I've been talking about the optimal hypothetical setup. But in my actual testing, I was limited to what was actually available, and I'll be discussing what that consists of. And since I don't actually have the inverter, I also emulated the inverter in all these tests. Now, I wanted to first pick a 12-hour day to simulate a sunny day and then later a cloudy day. So in this case, here's an example for a sunny day from 6 a.m. to 6 p.m. with obviously the highest amount of solar power at the peak of day, so around 12. Now here's an example of the testing methodology. Once again, this is an example for a sunny day and how that would look like at each level. First, I would simulate the solar panels. So once again, simulating a 12-hour day mapped out, and this will be the input power into the hybrid inverter. So say here we have in the morning, low to medium generation, peak from 9 to 3, highest amount of power, and 3 to 6, the lowest amount of power being inputted into the hybrid inverter system. Next, after knowing that, we want to know how much power is being required from the residential load. And now this will always be demanded regardless of the other three interfaces. So this is kind of independent. In this case, I chose for all my test systems to have medium loading in the morning, low amount of loading in the midday, and high amount of loading. And this is kind of to follow what would be for an everyday person, right? You're starting your day, everyone's getting ready for school or work, so about a medium in generation. Now during midday, everyone, I would assume, most people are going to be gone, either at work or school, so just less power is required. And then lastly, I chose high loading amount, or a high amount of power required from 3 to 6. Everyone's coming back home, people are cooking, washing, maybe watching TV, so just more power is required at the end of the day. After testing this, we can look into the battery. This will be looking at amount of battery power that will be given based on the residential load and the solar power. So in this case, we have the battery discharging because there's not enough solar energy since just a low amount, and we have a medium amount of loading. So the solar power can't supply the full need for the house, so the battery will step in. During the midday, the solar power has a lot of energy being outputted. So in this case, it can cover the low amount of power required by the residential load. And this extra power will go to the battery to help charge it, to be used for later. And once again, this later comes here. At the end of the day, when the battery is fully charged, it will start discharging since the solar power has less energy to provide, and the load is requiring a lot of power. And then lastly, that last kind of layer would be the AC grid. Now this follows a similar setup to the battery, but it kind of steps in as a last step. So in this case, in the morning, say the battery, is discharging and the solar power is also providing power, but there's still not enough to help supply this load. So in this case, the AC grid could step in and start sourcing to help provide the load. And then during midday, it might actually start sinking energy. So in this case, the solar power has more than enough energy to provide the residential load. It's charging the battery and it's giving power back to the grid. And then it also can just not step in at all. Say just the power from the battery discharging is enough to help supply the load along with the solar power energy. So now let's take a first look at one of the first layers. So in this case, the solar array panels. And for the solar array interface, I tested specifically the MPPT efficiency. Now, the MPPT, or maximum power point tracking, maximizes the power expectation from the solar array by continuously tracking and adjusting voltage and current to stay at peak of the PV curve. Now, this is typically done by the inverter, but in this case, I'll be emulating the inverter, so I'll have to manually adjust this point myself. And to emulate the inverter, I chose the IT6642C. This was just what was available. Now, for the actual test, I used the SAS software to configure a user-defined PV curve and user-defined irradiance and temperature curve that will simulate the conditions of the solar panel under the actual climate. And now for this whole entire test case, I used two different test cases. I simulated a sunny day and a cloudy day, and I'll be looking at the efficiencies of both of these days for the whole entire hybrid inverter system. Now let's take a closer look at what exactly is a PV curve. It is a power voltage characteristic curve defined by the user, or you can use the SAS software's pre-configured curves for various models for different solar arrays. But in this case, mine was included, so I just chose my own. Or sorry, I configured my own. Here is the configuration for the sunny day. Here would be the hypothetical or this pre-built one, but since I don't want to simulate for 12 hours, that's just too long, I made a user-defined irradiance and temperature curve to simulate for the sunny day for just a few minutes instead. Here's the table, and then here's how this table would look like to best simulate this curve over here. Now this is the same idea, but for a cloudy day. These little bumps would be kind of drops in the temperature and the amount of sunlight, so radiance. And this would be simulating, say, clouds are passing over the solar panels. And then here is what I actually used for my test, best emulating these kind of dips as seen here. Now let's take a look at the actual test running. So the irradiance and temperature curve, as it runs, the PV curve will also be changing over here. So the MPPT point will need to adjust to find the max power based on these values here. Now, since I was acting as the MPPT, I had to keep manually adjusting the current to best emulate the inverter as if I was the MPPT maximizing solar output. Now, after running that experiment, this is my MPPT results. As you can see, I wasn't as efficient as a typical hybrid inverter. Typically, it's around 96 to 97%, But in this case, for the sunny day, I was about 86% efficiency, and the cloudy day was about 83.1% efficiency. And I took these results and kind of condensed them to a 12-hour day, just kind of to map it out, to make it pretty clear. So as we can see, the graph increases in power with the increase in temperature in irradiance, and then later decreases. And now this will be kind of the power or input power utilized in the inverter system. Next, I wanted to test the inverter supply, or the inverter supplying power to the house. Now for the actual test, I used the 8206 to emulate the AC load and the 7921 EP to emulate the inverter. Now, to emulate the residential load, I wanted it to be dynamic and not the same power throughout the day. As mentioned before, medium to low, so around 200 watts, low power usage at around 100 watts, and then high usage at 400 watts at the end of the day. Now, to do this, I used a list file on the 8206 and calculated the load to, the 200, 100, and then 400 watts. So it would step through each of those sucking in that kind of power and seeing how that would look like. Now, the results show that the inverter is correctly able to provide power to the residential load. And we can also understand that the load requested will be unaffected by the input power from the solar panels. So it doesn't matter if it's sunny or cloudy, the house will still need power to run. Next, testing the inverter's ability to source or sink power from the battery. Now here for the actual setup, I use the 6642C. Since it has two channels, I used one as the battery emulation and the second as the inverter. Both of these tests will utilize the BSS software for battery emulation to emulate the chemistry of the lithium-ion battery for the charging and discharging curve. And here on the table, we can see that the negative current from the list will be sinking from the battery. And if it's positive, it means it's sourcing or charging the battery. Here we have showing the pre-configured battery emulation curve of the lithium-ion chemistry here that can be used for actual testing. And then for my actual test, I also created a user-defined battery emulation curve since the pre-built model didn't exactly scale to my voltage needs. Here we can see how the current corresponds with the list function and how it affects the state of charge. We can see the increase in state of charge corresponds with the current when it becomes negative here. And that means the battery is now sinking. The same can be said for the state of charge line as it's decreasing in slope. And since the current is positive, it means the battery is now sourcing. Now here we have the result of the charging and discharging of the batteries under the sunny day and the cloudy day simulation. Both show that they're providing power or discharging at the start of the day, corresponding to the load of the house, right? The medium amount of generation, and becomes to start discharging, right? Starts charging as it goes down here, because that means it's sinking power, since there's more solar power being provided. And then at the end of the day, during high power, we see it starts discharging at a much higher rate. And then the cloudy day follows a similar idea, but it's just more sporadic due to the rise and fall of solar power affected by the clouds. Lastly, I tested the inverter's ability to source and sink power from the residential grid. But as a quick reminder, the AC grid acts as a last layer in the system. And the inverter will begin to source or sink from the grid after considering power input from the solar array and the battery. Now, in my actual testing, after completing those 3 previous levels of testing, I concluded that my load needs were actually already met from the solar power and the battery system. So in my actual testing, I didn't include or test the residential grid. But in the hypothetical test, you could use the 7909 grid simulator and use that to best simulate the AC grid. Now with those 3 tests, here are my final results of those test systems. Here we can see the inverse relationship between the battery and solar power as they provide solar to the residential load. So over here, we can see solar power is increasing in a sunny day and reaches a peak over here. And at the same time, we can see the amount of power provided by the battery. So we can see it starts discharging over here as the solar power is starting up to help hit these 200 watts of power required by the load. And at one point, when the solar power reaches enough energy to actually provide to the battery, to the residential load, here's when we can see the battery start to charge, because there's more than enough power provided by the solar power to use the excess power to start charging the battery. And then later we can see once it dips underneath the required line by the load, that's when the battery starts discharging to help provide those needs met by the load. And the same idea in relationships is seen here during the cloudy day. Now let's take a look at the overall sunny day results. So this had an overall efficiency of about 94%. And now remembering the mission, which was how efficient can a hybrid inverter power be under different solar conditions. So in this case, we're going to look at sunny and then cloudy. Now here, this table shows the overall amount of power at each of these times. So here's the solar power, the residential load power required, and the battery power, whether it's sourcing or sinking. So if it's sourcing, it's positive, that means it's discharging. And if it's negative, that means it's starting to charge. And now we can also remember that efficiency is going to be calculated by power out over power out over the amount of input power. So in this case, the amount of input power will be provided by the battery over the output power, which will be the residential load here. So in this case, in the first row, we can see the only input is going to be the battery, since the solar hasn't even started getting energy or producing energy. So the inefficiency metric will just be the battery. Now over here, we can see that there's a bit of power provided by the solar. So now we have the inefficiency will be battery over the solar for the output of the residential load. And this has about a 99% efficiency. Now we can also see once the battery starts charging, the efficiency also drops. So in this case, when only the solar power is providing power to the residential load, we can see that efficiency seems to drop a lot. And so based on this table, my conclusion that I took away is that the inverter is more efficient at discharging rather than charging, is more efficient at discharging rather than charging, looking at the trend in efficiency. Now let's take a look at the overall cloudy day results. This had an average efficiency of about 91%. Once again, it follows the same kind of idea, and we can see the same kind of results. Once the battery is discharging here in the positive, we can see that the efficiency is much higher. But once the battery starts discharging over here, we can see the efficiency drops quite a bit, about 10 to 5%. And I took a similar conclusion away from here, that the inverter is more efficient at discharging rather than charging, looking at the trend of efficiency. Overall, additionally, the inverter also seems to be less efficient in simulating, a cloudy day rather than a sunny day. And I came to the conclusion that this is due to the sporadic power input from the solar array panel, and that the inverter may have a harder time producing more efficient or more power based on the sporadic input. Now, in conclusion, the hybrid solar inverter operated above 90% in both cases, but it did show that there was improvement in the overall system that can help improve efficiency when charging the battery system and when the solar input varies very quickly.